All right, hello everybody, and we're going to go ahead and jump into chapter 10. And to me, this is where things start to get kind of exciting, because now we are going to start doing what we call sequential logic circuits eventually. And we're going to start our discussion with a way to now, as I said in the Zoom, a way to now save a bit. So if we wanted to retain the state of some output or some input, we can put it through a flip-flop and retain it and save it. Okay. So the very base of what we're going to talk about today is called the SR flip-flop, and that stands for set and reset. So we call it the SR flip-flop. It's a simple data storage circuit, okay, and it's not like it has a memory location where it's going to store it like a hard drive, okay? If you notice in the picture here, the way that we're storing it is we're feeding back into, we got this cross-coupling back into the previous gates. So there's constant updating going on, right, if you can see that. So that's how we can retain the state, because we've got a constant feedback here. This is called the cross-coupled NOR scheme, and essentially all you have is two inputs. You've got a set and a reset. So what you're doing is you're either setting the output Q to 0 or to 1. Or I'm sorry, you're setting it to 1 or you're resetting the output to 0. So here's an example right here. So the set is 1 and the reset is 0. All right, if you follow that in here, 1 or 1 is 1. Negate that, you get a 0. Right? What happens down here? That 0 gets fed down into here, and you have 0 or 0 is 0, negate that, you get a 1. And that gets fed back to here. So you've got this constant feedback in what we call the cross-coupled scheme. There's also a cross-coupled NAND scheme, which we'll talk about as well. I would jot down both of these. If you were going to create a crib sheet for the final, I would have both of these written down and possibly recreate them for me. So if I ask for the cross-coupled NOR, if I ask for the cross-coupled NAND, this is what I'm talking about. So you can see over here now the opposite is true. The set is at 0 and the reset is high. So that's where we want to take Q to 0. If you have a 1, 0 here, set high, reset low, that gives you a high on the output, Q. And notice the Q is down here. The biggest mistake, if you draw this for me, excuse me, if you draw this for me on an exam, the biggest mistake is that you'll leave this one as a Q and this one is Q naught. Okay? So on the cross-coupled NOR, the Q is on the bottom. Okay? If you have a cross-coupled NAND, all right, we have two NANDs, we still feed back, we have a cross-coupled scheme, but we have these inversions out in front. Okay? So notice for the cross-coupled NAND, a couple things are different, right? With the cross-coupled NOR, you don't have any extra gates. You just have the two NOR gates, but Q is on the bottom. With the cross-coupled NAND, you have two inverters out front before it reaches the gates, and Q is on top here. Okay, so just remember that when you if you have to draw these for me. Okay, but you can construct either one with these simple gates, right? You don't need to buy an IC chip for it. It's a lot easier if you do, but you could create a data storage circuit using just the basic gates we've learned so far. So here's what it looks like. This is the function table for this setup. So we have a set and a reset possibility, and then we have a Q and a Q naught. And the Q and the Q naught should always be different. If they're not different, then you have this 1, 1 condition at the bottom. We don't use the 1, 1 condition on the inputs for an SR flip-flop. Okay, we only really use it for these three conditions here. So if you have 0, 0 on the input, that's what we call a hold condition. There's no change. So whatever Q was before, Q remains. Okay, and whatever Q naught was before, Q naught remains. If you have a set condition where the set is 1 and the reset is low, then Q, no matter what Q was before, Q now is 1 and Q naught is 0. Okay? If you have the flip side, if you have 0 set, or a low set and a high reset, that's a reset condition, and you would force Q low, which would mean Q naught would be high. Okay, those are the three conditions we use an SR flip-flop for, right? And just to reiterate, it's this cross-coupled scheme, this feedback, into each gate that gives us that ability to retain the state of some variable, okay? Or some bit, I should say, all right? And same thing. It's the same function table no matter which one you do. So this is table 10.1, and that's for this cross-coupled NAND. And then this is figure 10.2 out of your book, and it's got the exact same function. So we do not use the 1-1 condition. So I guarantee you I'll ask you something about this. You'll draw the truth table and label all 4 conditions, right? This last one, it's unused, not applicable, something like that. So let's look at the timing analysis of this, all right? These are the block. This is what you'll see in Quartus, all right? And so it puts the magic inside the box and just gives you the inputs and the outputs. It's kind of like a smaller version of what an IC chip would be, right? And now this one is just straight Q0 out. This one is Q and Q, and then there's an inversion. So sometimes you see them both ways. Sometimes, like some of the flip-flops in Quartus, you don't even have a Q0. If you want a Q0, you have to pull off a Q and then put a NOT gate there. Okay, that's how the JK flip-flop works, the JKFF. So this is the timing analysis. So all we're looking at is S and R and then seeing how Q responds, right? So initially, in this SR flip-flop, we have a set condition because set is high and reset is low, okay? So we are in set. All right, and so the next little section over here, we're now in a 0-0, which is a hold. So whatever Q was before, now Q is still. Okay, so it sort of locks it in, or if you want to think about it, it latches it in, so to speak. But it's in a hold condition, so it's not going to change. The next one, you have a 0-1, which is a reset condition, which is now going to pull that output low. All right. The next little time segment is another hold condition where we have 0-0. So whatever Q was before, and it was already low, it remains low until there's a change. The next change happens when we have a 0 or a 1-0, which is a set condition, and in which case you would pull the output high, no matter where it was before. All right. The next section, another 0-0, and so we've got a hold, right? So whatever Q was before, Q is again. And the next one has a big reset hump here, right? And so we've got 0-1, which is a reset condition. So wherever Q was, it pulls it down low. If it had already been low, then it would just stay low. Okay? And then we have another hold condition, a 0-0 here. And then finally we get to another set, 1-0, pulls it high, and then we end with a hold. So I should be able to give you S and R, and you should be able to give me Q based on your knowledge of this and what happens on the output. Okay? So I think that's pretty neat that we can start to retain the status of a bit. Right? And here's an example. So it says a storage register to remember the time of day when a temperature limit switch goes high. All right? Now, this is something I've never been able to figure out, is that we have a binary string here of 4 bits. 4 bits counts from 0, 0, 0, 0 to 1, 1, 1, 1. That's 15, or I'm sorry, that's 16 counts. So I've never figured out how they're representing the time of day with these bits. Okay, can't figure it out. Maybe they're just counting from 0 to 12, and then they go 0 to 12 again. I don't know. Or, I guess it would be 1 to 12. However they're doing it, okay? So somehow they're representing the time of day with these bits. And we don't know what's preceding these bits, but we're going to go on the assumption that what they're feeding us is the actual time of day. So we don't want to register that, and we don't want to remember it until that temperature limit switch goes high, right? So look at this setup here, right? This is sort of acting like that enable, right, to pass through whatever's on the other input. We talked about using, they're calling them strobe gates here, but, essentially what we called them was an enable, right, using the AND to enable some signal. So as long as the temperature switch is low, so this must be a normally open temperature switch, if you know anything about, normally open, normally closed. If at rest and it hasn't exceeded a certain temperature, it's at 0, that's a normally open or normally off. Okay? So at rest, it's off, which means it negates it doesn't matter what the time of day is. All of the outputs of this are going to be at 0. And we have the R here. We have all of this tied to ground at all times. So the only thing that's going to happen is it's going to go from a hold state in all 4 registers, or for this register, and then once that temperature limit switch goes high, it's going to pass through that time of day, and it's going to set whichever ones of these need to be set. So if it's 1, 0, 1, 1, then this Q will be set high, this one will stay low, this one will set high, this one will set high. And then we send that off to a microprocessor, and then we log, we data log that time of day that this happened, okay? And then we have this physical reset switch. So if we wanted to, we could put a high on the reset, and as long as this thing isn't high as well, if we assume that it's always low, if you just wanted to reset the whole thing back to 0, then you have a manual switch that you can, boop, just make high, and that'll put a 0, 1 on each one of these flip-flops and clear out the Q back to 0. Okay? But otherwise, these 4 AND gates are working like almost like a filter or like a gate, right? And if this temperature switch goes high, it's going to enable one side of that AND gate. And so then if this is 1, 0, 1, 1, you have 1, 1. That'll put a 1 down here. Here you have a 1, 0, which you still get a 0 out, and that'll be in a hold condition. Here you'd have 1, 1, and you'd have a 1 on the set. And here you'd have 1, 1, and have 1 on the set. Okay? So that's just an example of that. Now, we can get a little fancier with this, and we can turn the whole system on or off. Okay? And this is what is called a gated SR flip-flop. So here's the SR flip-flop right here. Okay? This is the cross-coupled NOR. Nothing has changed there. What's changed is we put these 2 AND gates out in front with this enable signal that says we're not even going to pass through set and reset unless this gate enable is high. When the gate enable is high, we're going to turn on the flip-flop and store that data. Okay? So this is another way. It's kind of another smaller way to look at what's going on here, okay? But anyway, the SR flip-flop is what you see inside this peach or orange, light red, light orange, whatever color that is, okay? That's the SR flip-flop we just talked about, and then this gate logic in front here makes it a gated SR. That changes it from an asynchronous flip-flop to a synchronous flip-flop. Synchronous can mean, and most often does mean, that it's triggered by some clock signal. Okay, that's usually what triggers something to count, because the clock signal goes high, low, high, low, high, low, over and over and over at a certain frequency. Asynchronous means the output immediately responds. So in this scenario, like if you just had the SR flip-flop, okay, if you put 1, 0 on here, however long it takes to propagate through there, it's going to change Q. All right. However, that's asynchronous operation. Here, you can't just change set and reset and operate this thing. You have to enable it first. So really, if you're talking about synchronous, it doesn't necessarily mean that it's time-based or that a clock signal is driving it. It just means that there's some outside control input that is turning this device or this circuit on or off. Okay? So synchronous means there's some control input. Asynchronous means the output immediately responds. There's no other conditions that are necessary. Okay? And so now we have a little bit bigger. We did just have the four condition SR flip-flop, and we still only use those, well, it's really the 3 condition, right, with the unused at the end. But if the gate is low, it doesn't matter what, we could put X's here, right? If the gate is low, S should have an X under it, and R should have an X under it, because it doesn't matter what those are. It's always going to be in a hold condition, because those front 2, those front 2 AND gates, when this is low, is going to produce a low. And that's going to be in a hold condition for all times until this thing goes high. And it doesn't matter what R and S do. Okay? When the gate is high and it passes S and R through, now it looks like a regular SR flip-flop. So if I could draw a line through the middle here, right? Again, 0, 0 condition, hold. 0, 1 is a reset. 1, 0 is a set. And then we don't use this last condition. Okay? So that's, you know, we just added some complexity to it, but now we've also added a way to control whether we want this thing to turn on or off. There's also another way to do this, and it's called a gated D flip-flop. What if you only have one data line and you want that, you know, when it goes high, you want it to be a set, and when you go low, you want it to be a reset, okay? The way you do that, if you only have one data line, is you put the data right into set, and then down here, you send it through a knot, and then so you always either have 0, 1, or 1, 0. There is no 0, 0. There is no hold condition. Okay, the only hold condition here is not really what we call a hold condition. We say that it is latched, okay? So we have this gate out in front, and if the gate is low, then S and R are not going to get passed through, which means that we're in a latched condition. So whatever Q was, we latch it into place, and it doesn't matter what D is. Okay, so we can see this here in this, and I love that Latches does this and goes segment by segment so you can see what's happening, okay? If the gate is high, the terminology that we use is that Q follows D. In other words, it's passing it through, okay? It's just passing it straight through to Q, all right? So if this goes high, this is high, and if this is low, this is low. Q follows D. When gate is low, we are in a latched condition. Okay. So let's look at this. So if I give you G and D, you should be able to give me the Q. So let's walk through this. Initially, the gate is high, so that means that this thing is enabled, and Q follows D. So you see the Q output here mimics exactly what happens on that D input. It's essentially passing it through, right? Then we go into a latched condition. So wherever Q was when this gate latches down, that's what remains. Now notice the D also stays high, but it goes low right here, and there's no response on the output because we're latched in. Now the gate goes high again, and Q follows D. So whatever D is doing now, we pick back up where we left off, and we mimic it until the gate goes back low, and we latch in. We were low down here, so that gets latched in. Okay? So now it doesn't matter that we go a high, low, high, right? Q just stays low because we're in a latch condition. Once the gate goes back high, now Q follows D, and we mimic what happens up here. And then we go back into a latch condition, and Q stays low. Okay? Anybody got any questions on this? If you can do what I just did with these and walk yourself through the timing analysis and say, I understand what's happening in this time segment and this time segment, and you go through here just like we did with the SR, I think you'll find that this is pretty straightforward, all right? But you got to get these basics down so that we can move forward and then start to use these flip-flops in bigger applications, okay? Any questions so far? I'm on low latency, so I'm only about 7 to 8 to 10 seconds delay. So, all right. All right, so the last one we're going to talk about is the master-slave JK flip-flop. Okay, and this is it works exactly the same. Well, not exactly the same because we're talking about hard drives, but you may have a setup in your PC where you have your master hard drive and you've got that one that supports it, that's the slave to the master, right? So if you look at this outside box, right, I'm going all the way around the solid line, okay? That's the outside of the box. And normally you just have the Q naught, the J, the clock pulse, and the K, all right? And you can see that down here. This is what they look, well, this is not what they look like in Quartus because Quartus does not have this Q naught down here. They expect you to pull a knot off of this Q if that's what you want, okay? So it operates first and then second, okay? And you can see how this happens. So initially, this kind of looks like, you know, we don't have the same, you know, cross-couple design, but that cross-couple design is both in the master and the slave here, okay? Those are just SR flip-flops. Can you see that? Right, S1, R1, that's an SR flip-flop. This is an SR flip-flop too. Okay, so we've got this gate circuitry in front here, so let's walk through this and see what happens. If the clock pulse is high, that's going to energize one terminal of each of these, right? and that's going to pass through J and K. So when the clock pulse is high, in this case, it's going to pass through J and K, and it's going to get loaded into this master flip-flop, okay? And it will change these Qs. So that's going to change the input on gates 3 and 4 here, right? Those outer gates. Notice what happens with the clock pulse. We send it through an inverter, and that becomes the input on those next AND gates, okay? So when the clock pulse is high, the master gets loaded, changes the Q and the input on 3 and 4. Then when the clock pulse goes low, it deactivates 1 and 2. The low gets sent through an inverter and becomes a high, and it activates 3 and 4. And so whatever Q was on here, Q and Q naught, now those get passed through to the slave SR flip-flop, okay? So it's this operation where we load the first one, and then we load the second one, and then we change the output, okay? Now we do this for a couple of reasons, right? And I'm going to show you the truth table shortly that explains why this happens, all right? And I'm not going to explain anything else about it just yet because I'm going to come back to it, okay? All right, so just to reiterate what I just said, when the clock pulse is high, gates 1 and 2 are enabled, the master flip-flop gets loaded, right? That's that operation right here. While that's happening, remember, if this is high and it gets sent through the inverter, that's a low. And so 3 and 4 are deactivated right now while 1 and 2 are activated, okay? Then the clock pulse goes low, 1 and 2 are now disabled, and 3 and 4 are disabled, and whatever was output from the flip-flop, from the master flip-flop, now gets loaded into the slave, okay? And then the cycle just repeats over and over and over and over. So we got the first part loaded and the second part loaded, and changes the output, okay? Now, something that we're going to start talking about is, the fact that we can have both what we call a positive edge clock pulse and a negative edge clock pulse. Right? And you can see the obvious difference between the two besides the bar over the CP, which, you're not going to get that. That's just a label out to the side. The difference between the two is that, number one, if it's edge triggered, you have this little triangle, okay? In both cases, these are edge triggered. In the previous example, down here, this is just a JK flip-flop. This is not edge triggered, all right? So if the clock pulse is high and J and K are changing while the clock pulse is high, then Q is going to change while the clock pulse is high, right? And so essentially it passes it through. And so that's more of a latch, right? And then when the clock pulse goes low, it changes, right? So this is not edge triggered right here. Now this one is. So the only time that these two flip-flops will accept the inputs of J and K are either on the positive side, if the clock pulse is transitioning from low to high, that's called a positive edge because you're on the rising edge, okay? It detects when that goes from low to high, and it only accepts it at that point in time, okay? So here's the problem. If you just have a regular JK flip-flop that's not edge triggered, like I said, when that clock pulse is high, you could get some noise on the line and cause Q to do things you don't want it to do, okay? If you're only accepting J and K at that one sliver of time where this is going from low to high, and then you have to wait for it to go back low, and then you have to wait for it to go back from low to high, that's the next time you take a sample, essentially. You accept J and K through to the internal master-slave operation there, okay? Now, as far as the negative edge, it's the same thing. There's something inside here that detects when that pulse goes from high to low, okay? So, most of the time we use the negative edge. And the reason why is the same reason why we use parity in error checking, because if you have, if you're only detecting when you go from low to high, then what happens if you have noise on the line? What if you have multiple spikes before the clock pulse? What if it's quicker than the clock pulse? Then you're going to have high, 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 right? And so you would have multiple edges, and it's going to advance this flip-flop based on what's on J and K. With a negative edge, you're detecting when it goes from high to low. And so this one better negates that potential error, okay, where you have the, because if you have a spike, I guess you could still have it, you could still have a spike here, but it is detecting the high to low, all right, and so this is what we typically use. All right, now here is the function table for a JK flip-flop, all right, so you'll notice that the first three look identical. If you're in a hold condition, you have 0, 0 on the input. If you have a set condition, you have 1 on J and a 0 on K. All right, and that gives you a 1 on the output and a 0 on the output. If you have a reset condition, that's 0, 1. 0 on J, K is 1. That means that Q is 0 and Q naught is high. Now, this one is what allows us to do a lot of our counting, right? And why we use JK flip-flops as opposed to just SR flip-flops. We can now use that 1, 1 condition to do a very useful function called, they're calling it the opposite state here, but it's the toggle condition. So if you have your flip-flopping toggle condition, and if you just leave it, like if you just tie J and K high to VCC and leave it in toggle condition, then the output is always going to be low, high, low, high, low, high, low, high. And it will be in sync with what the frequency is. Only something to write down would be that the frequency of the output, because remember, if you walk through this, it has to be loaded into the master, and then on the downside, in this case, if it's positive, right, it's going to take a high and a low to get from J to Q. Okay, so the frequency of the output is going to be 1/2 of whatever the clock pulse is. Okay, because it has to travel through 2 different flip-flops, and that takes an extra time period. So, if I have a clock pulse of 50 kilohertz, on my Q, if I have it in a toggle condition, it's going to be 25 kilohertz. So, you can kind of see where we would go with this eventually, where if you wanted to take, let's say you wanted to create a power supply, a 1 hertz, 1 pulse per second power supply. Well, you've got 60 hertz that's coming out of the wall, right? What if you could chop that down, divide it by 2, and then when we learn counters later, you can divide by whatever number you want. So let's say we divide that number by 6 to get it down to 10 hertz, right? Then we take a divide by 10 counter and knock that down to 1 hertz. Now we've essentially got a free power supply coming out of the outlet. We've got a, we can transform it into a square wave too and change it from a, when you get in 122, we'll talk more about the neat devices that you can use to make nice sharp edges off of a square wave. So, off of a sine wave. But anyway, we use this toggle condition all the time. All right? Any questions? Like I said, we're just scratching the surface. I want to tell you so much more, but I'm not going to fill your head with stuff I'm not going to test you on or quiz you on. I think we have enough here that I can do that now. Okay? Any questions? Any questions? Let's go ahead and just review real quick. So the SR flip-flop is a single-bit data storage circuit that can be used constructing basic gates if you would like. Adding gate-enabled circuitry makes it synchronous, so you need to know those two terms, asynchronous versus synchronous. And it says that means it will operate only under the control of a clock or, and this is a big or, an enable signal. All right, and that's the biggest thing I had to, because when you think of like synchronicity, when two things happen at the same time, right? Or when you have a crazy thought and you look and it's 11:11 and you go, wow, that's weird, synchronicity. There's a point in time where things happen. So synchronous just means that you have some kind of a control input. That's it. More than not, it's always a clock, okay? The D flip-flop cannot only utilize a set and reset because it can't have a 0-0 or a 1-1. It negates both of those because there's only one data input. So you can only either have 0-1 or 1-0. And then finally, the big one that we're going to be using is the JK flip-flop. And it's different than the SR. Well, for one thing, it's constructed of 2 SRs, right? So right off the bat, it's different. But the reason it's different and the biggest use we have for it is in the toggle operation. So that means that Q flips its opposite state. So it goes 1, 0, 1, 0, 1, 0. Like I said, that's in sync with whatever the clock pulse is. and it's 1/2 the frequency of whatever that clock pulse is. And the master-slave operation consists of 2 latches, one that receives the data while the clock is high, and then a slave that receives it while it's low. Okay, and that happens over and over and over again. Okay? Any questions? All right. Well, I appreciate you all coming in today, especially since we started so late. But look for my announcements later today. All right? And I will talk to you all later.